So in general, the rules for drawing the root locus, which derive from that angle condition and that magnitude condition, are the following. First, we locate open loop poles and zeros in the S-plane because they define where our locus starts and ends. We then determine the root locus on the real axis. We then determine the asymptotes of the root locus, that is, those zeros at infinity. In our case, we won't find the exact asymptotes. Rather, we're just going to approximate the asymptotes. We'll then find breakaway and break-in points, which again we won't find exactly, but we will just approximate. We won't determine the precise angles of departure and arrival, and we won't determine the precise location of where the root locus crosses the imaginary axis. So the rules that we're going to learn are just a sort of abbreviated way to draw a rough sketch of the root locus. If we want to understand in greater detail what the root locus looks like, then we'll use MATLAB. If you are interested to know for your own self what the procedure is for drawing a very precise root locus, you can refer to the book. And at this point, what these rules mean and what the precise terminology is might not make a lot of sense, but we will try and explain through the use of some examples. At this point, we'll now step through a quick example of how to draw the root locus by hand, or draw an approximate root locus by hand. This system is the one that we've already examined, where we, in essence, drew the root locus by brute force. And so in this case, I'm going to just quickly go through that root locus again in order to explain some of the terminology of the procedure. And then subsequently we'll do another example in a little more depth. So here's our approximate procedure. We want to draw the root locus, which is a graph of all the possible pole locations, closed loop pole locations, for values of k varied between 0 and infinity. And so the very first step is to locate the open loop poles and zeros in the S-plane. If you recall, the open loop pole, we had conjugate poles, one at -1 plus root 2j and -1 minus root 2j. And we had an open loop 0 of -2. And so this defines where the branches of our root locus begin. They begin at open loop poles and they end at open loop zeros. So that's step 1. Step 2 is to determine the root locus on the real axis. So if we look at the real axis, it's split up into kind of two regions. There's the part of the axis that's to the right of our 0, and there's the part of the axis that's to the left of our 0. It turns out that our root locus is only located to the left of the 0. And I'll explain subsequently how to determine that. So if you were to sub in points on the real axis over here into our angle condition or our magnitude condition, they wouldn't satisfy those relationships. However, if you picked a point over here, such as -3, it turns out there would be a value of k between 0 and infinity that satisfies the angle condition and the magnitude condition. Step 3 is to approximate the asymptotes of the root locus. And so if you recall, all branches start at open loop poles and end at open loop zeros. So one of our branches will start at an open loop pole and end at an open loop 0. However, we have more open loop poles than open loop zeros. So one of the branches starting at an open loop pole is going to go to a 0 at infinity, which is also called an asymptote. And it turns out, or if you recall, we have an asymptote that goes to the left along the real axis. So that's our asymptote. So as k becomes large, one of our poles is going to move out in that direction. Step 4 is to approximate breakaway and break-in points. So in this case, we have one branch starting at that open loop pole. We have another branch starting at that open loop pole. One of the branches is going to go to this asymptote. The other branch is going to go to the open loop 0. Okay. Where these arrows define how the poles move as we increase k. So here we're starting at k equals 0. As we increase k, the closed loop poles move. And as k approaches infinity, they move like this. This point where these two branches meet and then spread out along the real axis is called the break-in point. This break-in point defines where the two branches come together on the real axis. Breakaway points, consequently, are where two branches come together and break away from the real axis. Technically, you can have breakaway and break-in points that aren't on the real axis, but for the vast majority of cases they will be on the real axis. Step 5, which we won't do in this class, is to find the angles of arrival and departure. So this angle defining how the branch departs that open loop pole is called an angle of departure. Likewise, this is an angle of departure. So based on our rough approximation, we don't actually know that the root locus would go that direction. Technically, it could go flat or it could go underneath. But for our purposes, we're okay with not knowing precisely what the angle of departure is or the angle of arrival. Step 6 of the procedure, which we also won't do when we draw the locus by hand, is to find where the root locus crosses the imaginary axis. So in this case, there are no imaginary axis crossing. The root locus stays entirely in the left half of the complex plane. And what that means is that this closed loop system will be stable for all values of k. There are other systems that we'll see, however, that there are values of k for which the locus will move into the right-hand plane, where the real part of the closed loop poles are positive, which indicates that the system is unstable for those values of k. So at this point, we're going to go ahead and do a more detailed example where we get a little bit more specific about how to draw the different aspects of the root locus. So recall, the very first step is to locate the open loop poles and zeros. Looking at this negative feedback system, recall that the open loop transfer function is the loop transfer function. So it's everything in this loop. It's as if we took this feedback path, broke it away from the summing junction, and straightened it out. So the open loop transfer function is a gain times the quantity s plus 4 divided by the quantity s plus 1 times the quantity s squared plus 2s plus 2. And so just by inspection, we can very easily see that we have one open loop 0 is equal to negative 4. And then we can also see that we have 3 open loop poles because we have a third order denominator. One of the poles is easy to see. The pole due to this term is just negative 1. And then the poles due to this term are complex conjugate, and they can be found by applying the quadratic formula. Turns out that they're equal to negative 1 plus minus j. So these are our open loop zeros and our open loop poles. Once we've found those, we can go ahead and plot them. have an open loop pole at -1, have an open loop pole at -1 plus j, and an open loop pole at -1 minus j. And I'm indicating the open loop poles with these x's. We also have an open loop 0 at -4, where I'm indicating the open loop 0 with an O. These locations are important because we know that our root locus begins at open loop poles and approaches open loop zeros. So starting at k equals 0 and approaching k equals infinity. Step 2 of our procedure is to determine the root locus on the real axis. Okay. And this derives from the angle condition. So looking at this, I'll real quickly draw in our poles and our 0. Okay. What we can do basically is we can break the real axis up into 3 distinct regions. We have the region to the left of the 0, we have the region between the 0 and the pole, and we have the region to the right of the pole. And so we want to test each of these 3 regions by picking a point in each of those 3 regions and testing whether or not they satisfy the angle condition. Because we know that any value of s that's on our root locus, that is a closed loop pole location for some value of k between 0 and infinity, must satisfy both the angle condition and the magnitude condition. So for region A, we know that the angle of this complex number, when we pick some value of s and we plug it in to the open loop transfer function, it must equal -180 or some multiple of -180. And furthermore, if you think back to the very beginning of the class, if you looked at that review material about complex numbers, you may recall that when we're dividing 2 complex numbers, their angles subtract. So you can imagine them in sort of an exponential form or Euler form, where the angle of the numerator subtracts the angle of the denominator complex number. And so another way to think of this is these are angles from zeros, and these are angles from poles. So if we pick a test point out here in the A region and we draw an angle from the 0, you can see that the line drawn from the 0 to a test point in the region A is -180 degrees or +180 degrees. It's in that direction. So that's our only 0. Then we subtract angles from poles. And so in this case, if we draw a vector from this pole to our test point in the region A, it's also at an angle of 180 degrees because it's pointed that direction. We also have angles from these 2 poles. So you could imagine if we drew a vector to that test point, we have some angle θ1, and if we drew some vector from that open loop pole to that test point, we have some angle we can call θ2. You'll notice that this θ1 and this θ2 sum to 360 degrees. Okay. And since adding 360 degrees to an angle basically takes us back to the same angle, to the same location, we can disregard these conjugate poles that are off of the real axis, because their angles will always sum to 360. In essence, they always cancel. So we don't have to explicitly take them into account. So looking at the rest, we have 180 degrees subtracting 180 degrees plus, some multiple of 360. That sums to 0 or 360 or 720 or whatever. And think about, does this satisfy our angle condition? It does not, because what we need is for the angle to equal minus 180 degrees plus or minus some multiple of 360. 0 is not equal to minus 180 plus or minus some multiple of 360. So that means our root locus is not located in the region A. If we pick a test point here and sub it into our open loop transfer function, it will not satisfy the angle condition and the magnitude condition. It will not equal minus 1 over k for some value of k between 0 and infinity. We can then go ahead and test region B, where again we draw the angles from the numerator from the zeros and subtract angles from the poles. In this case, if we draw a vector from the 0 to the test point in the region B, that's at an angle of 0. And then if we draw an angle from the open loop pole at minus 1, that's to the left, so that's an angle of 180 degrees. We don't have to explicitly consider these conjugate poles because we know that their angles will always sum to 360. So 0 minus 180 is equal to minus 180 degrees. Thinking back to our angle condition, that does satisfy our angle condition. We needed it to equal minus 180 plus or minus some multiple of 360. So this will be part of our root locus, the region B. We then test a point in region C. Same condition. Look at the angles from zeros and subtract the angles from poles. So if we draw a vector from that 0 to a test point in region C, that's in that direction, which is equal to 0 degrees. If we draw a vector from the open loop pole, it's in the same direction, so it's also 0 degrees. 0 minus 0 is 0, which does not satisfy the angle condition, where we need to equal negative 180 plus or minus a multiple of 360. So going back to our previous slide, we have that our root locus includes this portion of the real axis. So there are values of k for which we can place closed loop poles in this region. So we can have closed loop poles that are real valued in between -1 and -4. But we can't have real valued poles that are greater than -4, and we can't have real valued poles that are less than -1 or greater than -1. Thinking back to the fact that branches start at open loop poles and end at open loop zeros, this is going to be one of our branches, where when k equals 0, the pole is located at -1, and as k gets larger, this closed loop pole will move from -1 to -4. We will then also have branches coming off of these open loop poles. So this procedure of applying the angle condition to test where on the real axis the root locus is located is a little tedious. You may have been able to recognize a pattern, and it turns out that in general branches lie to the left of an odd number of poles and zeros. So again, we don't have to consider poles and zeros that are off the real axis because they come in conjugate pairs and they cancel. So all we have to do is look at the poles and zeros on the real axis. Region A is to the left of 1, 2 elements, 1 pole and 1 zero. So since region A is to the left of 2, 2 is an even number, we have no locus in this region. If we look at region B, elements in region B are to the left of 1 pole, are to the left of 1 element. 1 is an odd number, so we do have a root locus in this region. And region C is to the left of no poles or zeros, so it's to the left of 0 elements, and 0 is an even number. So again, we have no root locus in this region. So this is a nice little shortcut if you don't want to go through applying the angle condition for every region. Step number 3 is to approximate asymptotes. If you recall, the number of asymptotes is in essence the number of zeros in infinity. So if we have 5 open loop poles and 2 open loop zeros, that means we have 3 more open loop poles than we do open loop zeros. And so those branches are going to go to zeros at infinity, i.e. our asymptotes. And so what we're going to do is we're going to just memorize the directions of these asymptotes for some basic cases. When we have 1 zero at infinity, this was the first example we saw where we had 2 poles and 1 zero. So 2 minus 1 gave us 1 asymptote. That asymptote went off to the left at minus 180 degrees, or positive 180 degrees. So when we have 1 asymptote, 1 zero at infinity, it'll always go to the left along the real axis. When we have 2 zeros at infinity, we'll have 1 asymptote going to plus 90 degrees and 1 asymptote going to negative 90 degrees. So we'll have something like this. When we have 3 zeros at infinity, we're going to continue this pattern of symmetry. So we'll have 1 at 60, 180, and 300 degrees. So we'll have 1 going up at 60, 1 going to 180, and 1 going to 300. When we have 4, then we similarly split up the 360 degree pie into four slices. So each of these, when we had 3, are 120 degrees apart. When we have 4, they're each 90 degrees apart. So we have 1 at 45, 135, 225, and 315. This pattern continues. So if we had 5, they split up the 360 degrees into five symmetric directions. Looking at this, we can memorize the directions of the asymptotes for each of these cases, and these will always be the directions of the asymptotes. What we won't solve for by hand, however, is the exact location of the asymptotes. So we'll know their directions but not their locations. We won't know where the asymptotes intersect the real axis. So technically we won't know if the asymptotes intersect in the left half plane, or if they intersect in the right half plane, or if these are centered, at -1, or if they're centered at +5. That we won't know. There is a way to calculate that. You can find it in your book, but for our purposes we're happy to just get a rough sketch of the root locus. Looking at the example that we started earlier, we have 1 zero, 1 open loop zero, and 3 open loop poles. So we have 3 poles and 1 0. We're going to have 2 asymptotes. We're going to have 2 zeros at infinity, and they'll go off at plus 90 and minus 90. So if we go back to our picture, we can go ahead and draw that in. So we know that our asymptotes will go at plus 90 and minus 90, but we don't know if the asymptotes will be located over here or over here. It turns out they're in the right half plane. So you'll have some asymptote going up at 90 degrees, and you'll have some asymptote going down at 90 degrees. And you'll end up with something like this. Okay. As you get a little bit more practice, you will start to sort of get a feel for what direction the branches are going to head in. If we want to know the precise location, we can go ahead and use MATLAB to draw the root locus. Continuing on with our procedure, step 4 is where we approximate breakaway and break-in points. This locus does not have any. In general, breakaway and break-in points occur when branches come together. In this case, we have no branches that come together. If you recall, we have a branch going that way, a branch going that way, and a branch going that way. So they never meet. In general, a good sort of thing to look for is that breakaway points, they tend to come between poles on the real axis, and break-in points tend to come between zeros on the real axis. Since we know that branches leave poles, you can sort of imagine 2 branches leaving 2 poles and meeting in the middle and breaking out. And since branches approach zeros, you can also imagine 2 branches meeting on the real axis and then breaking in to approach the zeros on the real axis. That might not be very clear. You can look at the first example we did to see an example of a break-in point between the 0 at -2 and the 0 at infinity. And in a minute we'll do another example that'll give another picture of what this situation means. Step 5 uses the angle condition to determine angles of departure and angles of arrival. So in this case we have these angles of departure. And step 6 is used to determine where the locus crosses the imaginary axis, and it uses the magnitude condition. And so again, we'll skip that when we draw things by hand, but it is important. So for example, in this root locus you can see that if you increase k enough, the closed loop poles will move from the left half plane into the right half plane. So this is a conditionally stable system. There are values of k for which we will place the closed loop poles in the right half plane and the system will be unstable. In order for us to examine these properties, we will use MATLAB. Okay. At this point, we'll go ahead and do another example. Recall step 1, locate the open loop poles and zeros. Okay. So this is the open loop transfer function. It has this constant k that we want to find how the closed loop poles vary with that k. The first step, we're told, is to locate open loop poles and zeros in the S-plane. So by inspection we can see that we have a 0 at -3. By inspection we can see that we have 4 poles, 1 at 0, 1 at -1, 1 at -2, and 1 at -4. Step 2 is to find where on the real axis the root locus is located. And so one approach is to apply the angle condition repeatedly to different regions of the real axis. The second approach is to look and see where on the real axis are we to the left of an odd number of poles and zeros. Okay, so we're looking for where the sum of the number of poles and zeros is odd. Step 3 is to locate asymptotes. So go ahead and look at our transfer function and think to yourself, will we have any asymptotes? How many asymptotes will we have? Okay, since we have 4 poles and 1 zero, we will have 4 minus 1. So 4 poles minus 1 zero equals 3 zeros at infinity. And we will memorize that this corresponds to directions of 60 degrees, 180 degrees, and 300 degrees, though we won't know exactly where these asymptotes intersect. Step 4 is to look for breakaway and break-in points. And it turns out, as I mentioned previously, that we will have breakaway points at locations between poles on the real axis. So you can sort of imagine this. So here's our real axis. We've got 0, minus 1 pole, minus 2 pole, got a 0 at minus 3, and then another pole at minus 4. So let's go ahead and skip back up to step 2 for a second. So the root locus will be located to the left of an odd number. So out here, we're to the left of no elements, 0 elements. 0 is an even number, so this part of the real axis is not on the root locus. In this region, we're to the left of 1 element, 1 pole, and since 1 is odd, we will have a root locus here. Here we're to the left of 2, 2 is even, no root locus. Here we're to the left of 3, 3 is odd, so we have root locus. And here we're to the left of 5. 1, 2, 3, 4, 5. 5 is odd, so we're to the left of the pole at -4. Looking at this, our branches start at open loop poles and go to open loop zeros. So that's a branch. As k increases, a closed loop pole will move from -2 towards -3. Here we have another branch that starts at -4, and it's going to go to a 0 at infinity at an asymptote, where one of our asymptotes goes to -180. Here we have 2 more poles where branches leave those poles. So you can imagine we have one branch leaving that pole at -1, one branch leaving that pole at 0, and at some point they're going to hit each other. They're going to bump into each other in between 0 and -1, and they're going to break out. So we have a breakout between 0 and -1. In general, when you have just 2 branches coming together like that, they will break out or break in at 90 degrees at right angles to one another. And these, once they break out, will then approach these 2 asymptotes. So the branch that started at -4 approached the asymptote at 180. The branch going up is going to approach the asymptote at 60 degrees. The branch going down will approach the asymptote at 300 degrees. and you'll get something that looks like that. I'll go ahead and redraw that a little bit better on the next slide. So step 1, locate poles and zeros. Pole, 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 0 at -3, and then another pole at -4. We locate the root locus on the real axis for step number 2. This is to the left of an odd, this is to the left of an odd, this is to the left of an odd. Step number 3 is to find the asymptotes. We have 4 poles, 1 0, so that means we must have 3 asymptotes. So that branch starts at that pole and goes to that 0. This branch needs to go to an asymptote at 180 degrees. These two are going to go, one to an asymptote at 60, one to an asymptote at 300. And between these 2 poles, we will have a breakout point. The branch leaves that pole, the branch leaves that pole, they bump into each other, they break out at 90 degrees, and they approach the asymptotes. So in general, we will know between which 2 poles we have a breakout, or between which 2 zeros we have a break-in, but we won't necessarily know the exact location. So it's not necessarily the case that the breakout point is at 0.5. The breakout point isn't necessarily halfway between the 2 poles. Again, there's an equation for calculating that location in the book, but for us it's just good enough to know between which 2 poles and which 2 zeros we have breakout and break-in points. Similarly, we won't calculate where this crosses, though we could determine it using MATLAB. In this case, all of our angles of departure and all of our angles of arrival are determined. So these are angles of departure where we leave poles. Here we have an angle of arrival where we approach a 0. And this is a rough sketch of a root locus. It's not exact, but we can tell quite a bit from it, and we were able to draw it relatively quickly. Always remember to put arrows indicating the directions that the poles are moving, where we start at small values of k approaching 0, and we move in the direction of increasing k. So this brings us to the conclusion of Module 17. In this module, we learned about the root locus tool, which is a graphical tool for visualizing all the possible closed-loop pole locations for a given parameter change, for example, a proportional gain k. We learned how to draw this root locus based on angle and magnitude conditions from the Openloop transfer function. So this is quite interesting that we can draw this root locus, this picture of all the possible closed-loop pole locations without ever actually finding the closed-loop transfer function. We draw it straight from the Openloop transfer function. And while we learned what the angle and magnitude condition were, that's really not what's most important for us. What's most important is this procedure that we learned in order to draw a very approximate picture of the root locus. If we want to draw a more exact picture, then we use some sort of software tool like MATLAB.